course on FPGA based signal processing systems. We are doing the design of FIR filters using the window method. So choosing the different windows and what is the relation between the transition band and the ripples with respect to the window characteristics. So we have taken in this example of low pass filter design using the rectangular window of 9 samples, and the cutoff frequency is 1.5 radians per second. So for this filter we had obtained the coefficients, and first what is the HD of e power j omega. From that, what is HD of n is obtained with the integration, and when HD of n function, and then multiply that HD of n with the window function, rectangular function, and then get the h of n. So h of n coefficients were manually calculated for this. You could have observed this midpoint symmetric coefficients among these, the relation between them. So the using the FDA tool of this MATLAB, using the filter designer. So if you type this in the filter designer in the command window, so you can get the same response. I would like to show you that if the order of the filter increases, then manual calculation of filter coefficients would be cumbersome. So in that case, you can use the filter design tools and then get the coefficients. So once you get the coefficients, that coefficients can be fed to the Verilog module, and the Verilog module can perform take the coefficients and then give the response. So here with the designer tool, I have just cropped this from the MATLAB designer tool, in which there are, you can specify the structure, order, and so on. So the response type, which is low pass filter, here you have the choice of low pass filter, high pass filter, band pass filter, band stop, and we want to design a differentiator. All the choices are available. Also the design method, I have chosen the FIR with the window method. So you have these choices again in the FIR filter design as well. So the FIR window method, and specify the order. N is 9 over there, so the order is n minus 1. I specified it 8, and the window type, you can choose the rectangular window, Han or Hamming or whatever. The design to verify the coefficients, we have taken this rectangular window, and the unit hertz here, cutoff frequency 1.5, that is omega c radians per second. So 1 by 2 pi, 1.5 by 2 pi had put, and the fs is 1 over here. So from this, it is showing the cutoff attenuation at cutoff frequency fixed at 6 dB in this half the passband gain in the tool. Okay, so the filter response, which we got exactly the same as that what I had shown with the in the previous lecture, with the plotting the cost function, that is the coefficients obtained, and with the generalized coefficient h of n generalized equation, and the same response we could get it over here as well. So we can see this is 300 millihertz around, and then here it was 0.3 representation here. So you can see the response in this also, same then, and the phase response also. So you can see the phase response change over here. So this is the design, and can we get the coefficient from this? We want the, for this particular specification here, the ripple specification is not given. We can also if you specify that what would be the ripple, we can specify that even. So getting this, after that we just would like to give you the coefficients what we get for this. So the coefficients are like, you can observe that what we have exactly obtained this 4 digit 0.0222 and 0.1037, which is also symmetric about 0.1037 in that case. And you see the h of 4, what we have got 0.4774, and similarly 0.3175 and 0.3175, this is getting repeated here. So you have the 3, 6, 9 coefficients, okay, so which is symmetric about, midpoint symmetric about that. So odd length. So the filter coefficients can be obtained from one of the windows here. You can we can check this here. If you click on that, you would be getting the filter coefficients. This filter coefficient. From that filter coefficients, you can also observe that there is a the impulse response. So the impulse response is same as filter coefficients, as we have learned to that. So when we convolve it with the impulse input and the coefficient, you will get the impulse response same as the filter coefficient. So that's why this impulse response is nothing but the filter coefficient. So you can see the midpoint symmetric one, h of 4, which is over here 0.47. So this is obtained by just clicking over here in the FDA. That's an impulse response. So 0.317, also here you get the impulse response, and the next one 0.02, okay, and then the negative ones also same, and then 0.02 here. So 9 coefficients which is showing the impulse response. So the same thing we will be getting it through the Verilog module also. After writing the code using these coefficients and the step response. So if you give the step response, you can take it from in the FDA design. So given the filter response, this is going to be settling at 1. After this is the step response of the, if you give the step input to this filter, what would be the response? Okay, so if you give the impulse input to this filter, what would be the response? Okay, so that's what this curves this shows here. So you can get the filter coefficients, step response, as well as impulse response, and the filter coefficients also. So the other options have this magnitude and the phase response as well. So again, so either you get the coefficients manually by calculating that the filter order is more, then it would be difficult, but for the smaller order you can always get it, like for the eighth order, which for this example we have got it. Then use these type of tools, any of the tools, to get the filter coefficients and say get the coefficients, and then use this coefficient in your Verilog module. So this is one, and after obtaining, so for the same problem we have got the response as well as the coefficient. So getting into the a few of the problems, so how to go with the ripple. So in the previous case there is no ripple allow specification given in the problem. So if we design FIR linear phase low pass filter characteristics and its specifications are given here. So you can allow this h of e power j omega, in which this is also a low pass filter, so in which you have, this is the response omega, and here you have this 1 plus delta p, and this is 1 minus delta p. So the cutoff frequency is exactly omega c over here, and the passband frequency is omega p, and the stop band frequency is here. So this is the case of delta s. Okay, so this specification, what does it give? So here 0 to 0.19 pi. So this is the passband 0.19 pi here, and the 0.21 stop band starts 0.21 pi. Okay, so up to pi this is drawn. So for this case, and the h of e power j omega, the desired one, this is the filter specification given 0.99, this is 0.99 to 1.01. So the allowed ripple is 0.01 both the sides. Okay, so delta s is 0.01 here, the allowed ripple 0.01. Okay, so if these are these specifications, and you can easily find omega c, that is 0.19 plus 0.21 at the midpoint of it by 2. So the equivalent here, the 1 plus 0.0 delta p is known, and delta s is known, and omega p is known, and omega c is known. With this, there is no number of samples in the window, or window specification is not there. So just it is given to design this h of e power j omega with omega having the characteristics this. Okay, so this is the characteristic. So from this desired one, so first we will take out the ripples. Okay, so it is 0.01 at the attenuation band. So 0.01 from here, this is allowed as 0.01, and in the passband also 0.01, 1 plus 0.01 and 1 minus 0.01. So look at this attenuation at the one, it is 20 log, take the 0.01. Okay, or choose if the ripples are given in the passband and stop band in different ways. Suppose it is 0.05 and 1.05. So ripple is allowed more, and here in the stop band ripple is less. So go for the minimum ripple in the design. So 20 log 0.01 here, it is minus 40 dB. If you calculate this in the dB, it is going to be minus 40 dB allowed. So stop band attenuation should be 40 dB here. So with this, then which window we can choose for this case? So if we go to the table of that rectangular, Hanning, Hamming, and there is a, this specifies the transition width. Transition width is it's in frequency, del f. The relation is 0.99 by n. If you remember, just recall the expression we got it for the main lobe width. Okay, so and then from this transition width is obtained here. Transition width, which is decided from the main lobe width of the window function. So here main lobe to side lobe rectangular is giving minus 13.3 dB here. So this is from that table. So this is new here in the transition width is for how much it in transition width is what is the relation between n number of samples or in the n, and then what is the relation between this transition width. The peak side lobe, which is 21 dB below, here 44 dB below. So you can achieve this Hanning. So this our display 53 here minus 74 here. If we consider this, it is 40 dB required. So this can give minus 44 dB. So we can choose this Hann window. So Hanning window can give this at stop band attenuation of at least 44 dB. So that's more than minus 40 dB. So we can choose around this, or further you can choose Hamming as well for lesser and lesser 53 dB. So by choosing this window, for the specification which is given over here, transition width is from this expression from here, the transition width omega p to omega s. Okay, so what is the transition width in this design? So transition width omega s minus omega p, which is 0.21 and 0.1 pi, which is coming to 0.02 pi. So calculate them and find the by 2 pi, which gives the transition width of 0.01. So for the Hann window, we have n into delta f, which is 3.1 by n. Okay, so you can find the order easily. That order is 310. So 310, you see the order of the filter is 310, then it would be cumbersome to find all the coefficients, right? So in these cases, you can use the tools to give the coefficient and the response. Okay, so this is finding the order n is 310. So how do we get the filter coefficients here? So what is the omega c is omega p plus omega s by 2, which is 0.2 pi. Cutoff frequency is here between 0.19 and 0.21, and alpha, the phase response, the group delay, the thing is equal to n by 2, 310 by 2, that is 155. So the slope of this phase characteristics that would vary with respect to omega. So 155 we get because this is the n is even order here. In the previous case it was odd order, so n minus 1 by 2 we took, 9 minus 1 by 2 it was 4. If you recall, here this is 310, so get to this n by 2 which is 155. So what is hd of n? That is hd of e power j omega, and getting the inverse Fourier gives that hd of n, just sine of omega c. This is a standard expression for this omega c, n minus alpha, and pi into n minus alpha. So substituting this is sine omega c n minus alpha by pi into n minus alpha, that is hd of n. From this hd of n, we can get h of n, which is hd of n into the Hann window expression needs to be multiplied. So we can get the coefficients here by substituting n and substituting n for various values. Okay, so using this expression, we can end up with the h of n. Okay, so h of n of this is 310 anyway. It is going to be more coefficients, so we didn't calculate it with manually. So this can be obtained through the designer tools, filter designer tool. So here is this example which doesn't specify the window function, and which this is having the only the ripples allowed in the passband and the stop band. Here luckily this is both the allowed ripples are same, 0.01 and 0.01. So if it is different, go for the take the lowest ripple allowed in the case of passband or stop band, and find the transition width. From the transition width you can get the order n. If we once you know the order, the standard for the low pass filter, this is the one, and HD of n, the expression is this omega c into n minus alpha can be calculated. Once you know the n, the alpha can be calculated and HD of n can get. So this h of n can be obtained by having the window function. The windowed HD of n is the that's response of the or coefficients you can obtain from this. So that if you get the coefficients and then get to use this coefficients in the generalized formula and plot the response. Give the specification in the designer tool and get them coefficients also and the frequency response even. So this response can be how this and then use this filter coefficients in our Verilog module. So this is another example which is having the design of FER filter with n equal to 24. Here is that if we have order is specified, filter order is specified, given is we use this n minus 1 is the order. So here order is specified taking this n is 24. The frequency response of the filter desired one h of e by j omega is 1 for omega equal to up to 0.2 pi, and it is 0 from 0.2 pi to pi. So the response is like this actually here, and then cut off here. So this is 1. This is what is desired at 0.2 pi exactly here, 0.2 pi to pi, this is 0, completely 0 over here. So ideal response which should be designed with n equal order 24. So what is the passband frequency? Only one frequency is given, which is 0.2 pi, and the n is so 24. So alpha is because even order, then it is going to be divided by 2, 12. Once we know this alpha 24 by 2 called, this is HD of n is sine omega c. This is the, you can see here this omega c is that is taken as omega p itself. There is no omega p and omega s, that is passband and stopband frequencies are not given, radiant frequencies anyway. So these are not given. If both are specified, you can get the omega c from that. Otherwise consider this omega c, what is omega c as omega p only, whatever given over here in the ideal response. So this is 0.25, n minus 12 is alpha is 12 here at pi into n minus 12. So this is HD of n. So once we know this HD of n, again you can have the for the rectangular window. So given ideal response, this is response here, there is no ripple specification is there, only order specified in this case. Okay, so for a rectangular function, can we get this? Okay, so what is it? How can we get that ideal one? Okay, so using the rectangular window, so delta omega is 2 pi 0.9 by n, n is 24 here. The relation between this we can obtain from the table, this one, that is a transition width, this is del f from the table. Okay, 2 pi del f, so which results in the transition width of 0.075 pi. 0.075 pi, and so if you use this HD of n and into the W of n, the window function, right? So you get this h of n. So h of n is sine omega c, again omega c is omega p itself here, 0.2 pi n minus alpha by pi into n minus alpha here up to 0 to 24. Otherwise this coefficients, you can get the coefficients of this. From this we can see the obtained coefficients for the rectangular window, which results in the transition band. So this is not, so the transition band is not straight here, it is 0.075 pi. Okay. And the stop band attenuation correspond to the rectangular window is 21 dB. So if you calculate what should be the ripple allowed here, so ripple specification is not given in this case. The ideally, so because of the using rectangular window, what should be the 20 log of del s is minus 21 that dB from the stop band attenuation from the table again. So delta s is 0.089. So its allowed ripple is 0.089 here. Okay, so this is 0.089, del S is given 0.089. So this is with the rectangular window, but we were not able to exactly achieve the specification, which is going to be not ideal as specified here. There is a transition width. In order to reduce this transition width, we have to choose either, I mean, this transition width is related to the main lobe of the rectangular window. So to reduce this one, so can we go for some other window function, or suppose, or increase the number of samples in the window only. So the increasing the number of samples in the window function can reduce this width, but let us see, suppose we choose some other window function which would result in what happened in the Hamming window, for a Hamming window suppose. So here h of n is this into Hamming window function 0.54 minus 0.46 into cos 2 pi n by n. Okay. So Hamming window, which is giving minus 53 dB from the table, stopband attenuation is 53 dB, whereas here this is 21 dB. So if we go for the reduction in the preferring for 0.0889 ripples, let's see what happens to the ripple and the transition width. So, if we look at here, the stop band attenuation is minus 53 dB and 20 log del S equal to minus 53, the stop band attenuation. Finding this, yes, it's the reduction 0.0022, which is good compared to the 0.089 the ripple or the stop band, choosing the Hamming window for this design. Yes, but what happens to the transition width? This del omega is equal to 2 pi, and the del F, which is going to be 3.3 by 2 n. So 3.3 by 24 results in 0.275 pi. So whereas in the previous case it is 0.075. So still wider, this allows the case of, yes, the ripples are good, reduced now 0.00222. The ripple here is less, h of e power j omega here, and this is omega, but the transition width has become wider now. It is 0.275 pi. Yes, of course, because of the rectangular window has the main lobe, rectangular window has the, and the Hamming window, if you take the main lobe of it, this is main lobe is more compared to the rectangular window of the main lobe of the rectangular window. So this main lobe increases this transition width, but it has a good stop band attenuation, so it reduces the ripple. So that can be easily seen in the design. So then what should be the compromise here? So choose this Hamming window, and if you want to reduce this transition width, then if the order is not fixed, okay, so then we can go for a better increase n and reduce the transition width. Okay, so likewise we have to the filter specification accordingly. We need to choose the window function and the calculate this ripples and the transition width, transition bandwidth here. So the compromise needs to be made between, or the trade-off, which window function. So as we discussed in the previous lecture, that one is because of the main lobe and the relation, main lobe and the transition width relation. The transition width are directly proportional. So but main lobe increases as we go for the tapering windows, but the side lobe level is reduced. The attenuation is good. The ripples, the ripple amplitude is very less here. Either we have to choose the we have to stick with one of this, any of the, yes, it's good that ripple attenuation is the focus, then keep it and adjust the number of samples in the window function. So this is how it could be managed. We here with the design can be made. So the order here, order is fixed. So for the given order we can have the either a increase in transition with Hamming window, or with reduced transition width, the ripple will be more in this case using the rectangular window. These are the, even further if you choose the other window functions, as also further and further you can have this Blackman window, which can even reduce the ripple little, I mean further 74 dB, it could be 74 further, but again the transition width will be of will be more. So the design needs to be taken care with which window function, and it depends on the specification. So specifications can be from these examples, which we could say, if the specifications can be of the ripples, del S, what is the stop band attenuation or the ripple allowed in the stop band, and the cutoff frequency, pass band and stop band frequency. Using this, or the order can be fixed, filter order can be fixed with that, or the response, if the response is the specification which is needed, then these all the parameters are required for the design. This is for the low pass filter case. But if the order and the filter specification are only the ideal, the two cases, or third one would be the ideal filter response. So the ideal filter response, in which we could not get this ideal response, as we said, this is unrealizable. So when we try to design this filter, either you will have this, all of them, the pass band ripple, stop band ripple, and the transition width, and the cutoff cannot be sharp like as such. The order needs to be further and further increased in that case. This is for the low pass filter. So if we have the band pass filter, for example, here the space, yes. So case of band pass, the response can have this ripples over in there, and then there is a stop band and the pass band, and if you have this omega h of e power j omega. So this is the pass band, and here you would have this omega c1, the cutoff, and omega c2, the another cutoff frequency. So the pass band omega p1, and this is omega p2, and here omega s to stop band, here again omega s1. So it starts like that. So the pass band is this. Okay, so the pass band ripple over here, and you will have the stop band ripple delta is 1 and delta is 2. Okay, so this is delta p 1 plus delta p and 1 minus delta p. So the specification will be different in this case of, suppose it's a band pass filter, and again HD of an expression will have the two cutoff frequencies, omega c1, sine of omega c1 n minus alpha by pi minus pi into n minus alpha minus omega c2, or omega c2 minus omega c1. So there will be two expressions for the band pass filter if you integrate it for the given h of e power j omega. H of e power j omega is the desired one. Okay, so here the specification what is needed here. So here this is the one. So it has the specific band pass filter will be similarly can be designed with the considering the stop band attenuation of the filter, which filters use rectangular, Hahn or Hamming or Blackman, the famous four of them. Also, if you choose the Kaiser window, that would be different. The tunable parameters we can get using that. So low pass and the band pass filter, you can have the high pass as well. High pass filter, which is having the one to this. So you can have the pass band ripple as well as the stop band ripple over here. In case of high pass, it can be designed also. So with the given specification, get the HD of n, choose the window function, and then multiply them. You get from the HD of n and the h, we can get the h of n, which is the realizable one, and the filter order can be computed, transition width can be computed, and the specifications also can meet out the ripple how much ripple allowed in the pass band and stop band. So this is giving the design of the filter, how the filter design can be done. But so using these filter coefficients, we will be making a Verilog module, and the expression of having this x of n in the case of FIR filter. Suppose if H of 0, H of 1 in the linear filter, this linear phase configuration, H of 2, and for example up to H of 3. So can we have this, how do we, this structure, how do we code them in the Verilog? If you have the linear response, linear phase response H0 and H3 and H2 and H1 are same. So the H0 and H3 will be same and H1 and H2 will be same in that case. So this filter structure, how do we code it in the Verilog? Okay, so that we will discuss how to make the Verilog module, how to get the step response and the impulse response as we got it through the FDA tool. We'll discuss that in the next lecture. Thank you.